All right, 5.3 is concavity and points of inflection. So what you want to remember here, what we're doing is curve sketching this chapter. So we are examining characteristics of equations to find out points and intervals of increase, decrease, maximum, minimums, asymptotes, intercepts, all that sort of stuff. We're piecing all this together to be able to accurately curve a sketch just given an equation. No technology, no just plotting points and connecting dots. We want more accurate characteristics of the graph. So what we're going to talk about today is concavity and how we can use calculus to determine intervals of concavity. Now, if you think about concavity, you know about this from pre-calculus. Concavity means concave up or concave down. So concavity, you remember from working with quadratics or the parabolas, can be concave up or concave down, okay? Concave down. Now, concave up, you would have a parabola that opens upward, right? It's up like a cup. When you see the graph, it opens up. Concave down is down like a frown, okay? It's opening down like an umbrella. Everything is kind of turned down. So you remember this from pre-calculus. Now, if we have a strange function that varies, goes up and down and all this sort of stuff, there will be intervals where the graph may be concave up, and there may be intervals where the graph is concave down. In a parabola, because it's only degree 2, it's always concave up or always concave down, but not necessarily true when we're talking about just a regular kind of like a complicated graph. So the diagrams are such here that you want to remember that from A to B, there's different ways the line can be connected from A to B, according to the graph. If the line connects from A to B in this way, is that out in the hall? Thank you. Then if the line is down here and curves upwards towards B, that is concave up, okay? Because you can envision this as part of a parabola that opens up, okay? So if it's part of a parabola that opens up, if you can envision it that way, then yeah, that's concave up. This is concave down, the connection from A to B. If there is a bow in it that kind of bows up from A to B, if it kind of rises up a little bit like that, then this would be concave downward, because this would be a section that would be part of a parabola that opens downward. Think about it that way, okay? So the graph vision of concave up and down is something you're familiar with, okay? What we want to notice here as well are the derivatives that are drawn here. Okay, you see the derivatives here? And we, of course, in calculus, we're very interested in the derivatives. We've talked about the first derivative test, right? Where we can identify where the graph is increasing, all right? That's where all the derivatives are positive. That's the graph is increasing. The y values are getting larger. The derivatives are all positive. Now, if the derivatives here, let's take a look at the derivatives, what's happening here. So I have a derivative with a slope here, a derivative with a different slope here, and a derivative with a different slope here, okay? So we want to examine what's happening with those slopes between A and B versus what's happening to the slopes between A and B here. Okay? Now, they're both positive. The derivatives are positive here in both cases. Okay? So the first derivative is positive here. Why? Because the slopes are all positive value. And here, the first derivative, it's all positive here too. So the first derivative does not give us any kind of hint as to what's going on with concavity. It's not the first derivative. Okay? So what we have to think about is something further. Now, let me just move to this diagram here where we have different regions. And you can sketch this if you want, close as possible, or you can just watch, okay? Just watch as to what I'm explaining here. You don't have to copy this down exactly. But if you just watch and learn here, this will be good for you. So let's consider between -4 and +1 this graph. Obviously, the graph is decreasing for part of it, and then it's increasing again. And that kind of gives us a hint as to, you know what, it's not just the first derivative we're looking at, because the first derivative changes here from negative to positive. So we can see that from -4 to 1, hopefully you can see this, that the concavity of the graph here is what? Concave up or down? It's one of those two. What is it? It is concave up. Even though it's hard to see, it looks kind of flat here, it's it's concave up. Okay, it's up like a cup. So what is happening to the derivatives? If I'm going to draw a bunch of derivatives here, okay, and these are not very good straight lines, I'm sorry, but what's happening to the derivatives here? How are they changing from -4 to +1? How are they changing? How can you describe what's happening to the first derivatives there? Anyone? Decreasing, okay? Well, the slope of this one might be a negative something, maybe a -5. The slope of this one is still going to be negative, but it's not going to be as negative, right? It's a little flatter, so this might be -1. This one down here, right here, this is slope of 0, and this one might be slope of 2, let's say. So they're not decreasing. They're actually increasing. The values of the slopes are increasing. So they are changing in such a way from negative to positive. They're getting larger, okay? So yes, the first derivative slopes, okay, the first derivative is increasing, okay, increasing from -4 to 1. We can see that, all right? And that's where it's concave up, okay? Well, let's examine this a little bit further then. For example, can you see that between P and Q, this is a concave down section? Everybody see that? It's concave down like this, okay? So what's happening to the slopes here? If we start at P, that's a positive slope. This is 0, and this slope is negative. Now, what the first derivative test told us that, what do we have between P and Q here? What do we have between P and Q when we have a positive slope, a 0 slope, and then a negative slope? Do you remember? I think this is from chapter 4, right? So you got a test coming up on this tomorrow, right? So you should know this. What's happening? What does this tell us? That somewhere in between 1 and 3 we have a what?
Local max.
Thank you. Local max. You see this? Local max? Positive, then 0 slope, then negative. That's a local max. Okay. So what's happening to the slope here? If you just consider the values of the slopes, we have a positive, maybe +2. We have a 0, and then we have a -1 right here. So positive to negative, those slopes are decreasing. Okay? And similarly, here, they are getting larger and larger and larger. Okay? Here, technically, we've got a large negative. These are getting larger as well here. And then here, on this, from R on, they're getting smaller as we go from left to right. So as we move from left to right, are the derivatives increasing or decreasing? That is what we're focusing on. Now, the rate of change, here's something very important. The rate of change of the derivative is what? Sorry? Second derivative, thank you. The rate of change of the rate of change. Okay, remember that from last chapter? The rate of change of the rate of change, that's the instantaneous rate of change of the instantaneous rate of change, second derivative. So how is the first derivative changing? Well, we can examine the second derivative and see how the first derivative is changing. So the key to concavity is going to be the second derivative, and we'll get to that in a second, okay? The key to concavity is going to be the second derivative. We need to see how the first derivative is changing over time, or changing as we move from left to right. Now, point of inflection. I need to talk to you about the point of inflection. So the point of inflection, we have a point of inflection here at P, and at Q, and at R. So these points that are listed on the graph are special points. These are points of inflection. Knowing that those are points of inflection, how would you describe or define a point of inflection? Anyone see what was happening there at those points?
Changes from concave, it changes concavity.
Okay, yes, it changes concavity, that's exactly right. So a point of inflection, the graph changes concavity. It's absolutely right. The graph changes concavity. So we go from concave up here. And at P, this switches to concave down. It's concave down here till Q. At Q, it switches to concave up. Now, this is not a point of concavity right here. Okay, so we'll talk about this. That's a kind of a special part of the graph, right? That's a cusp. Remember, we talked about that earlier in the course. So this concavity does not change actually here. It's still concave up here. But this is something we'll talk about a little bit later. Okay, so there's no change in concavity there. It's increasing, and it's also increasing over here. But at R, we do have a change of concavity. So either change of concavity from positive, concave up, or negative, concave down. Okay, so point of inflection where the graph changes concavity. Any questions so far? Any questions at all related to what I've talked about in the last 10 minutes here? Good so far? Okay. If you're picking up what I'm putting down here so far, then we'll move on, and you should be good. Now, let's bring it back to concavity and second derivative, okay? So as we mentioned before, the concavity is dictated by the rate of change of the first derivative. So what is happening to the first derivative as we move from left to right? If the first derivative seems to be getting larger and larger, that means that the graph has a concavity of up, okay? It's concave up in that section, which means that the second derivative, okay, that is the rate of change of the first derivative, is greater than 0 or is positive, okay? What's another way to put that? I'll write that down. Rate of change of first derivative is positive, or the first derivative values are increasing from left to right. Okay? So the rate of change of the first derivative is positive. That means it's increasing, or the first derivative values are increasing, okay? So if the second derivative is positive, we know that the first derivatives are increasing on that interval, and we know that the concavity is concave up, okay? So this is the key point right here, where the second derivative is positive, that's where we have concave up. Similarly, where the second derivative is negative. Whoa, wait, what? Oh, negative slope, positive. Oh, sorry, this is an example of the same thing. So this is increasing. These are also increasing. So this is just another instance. Sorry, I thought this was decreasing. I didn't look carefully. This also has a second derivative of positive, even though we have a local minimum here. And that's going to actually come into play really heavily later. Okay. You'll find that, well, we'll talk about the second derivative test, I think, next section. Okay, the second derivative test. There's a second derivative test. And what does that tell us? Well, you can see that the slopes are increasing here. This is still concave up. Okay? So that's for both of those graphs. All right? Here is where we highlight the second part here. And this is, again, from your textbook, Red Stewart Calculus, the first course. And in this little box, the test for concavity, this summarizes, here's the negative part here, okay? So if the second derivative is negative, that means that the rate of change of the first derivative is negative or decreasing. So that means the values of the first derivative, so as you look at the board here, the values as they are decreasing, okay, the slopes are decreasing from positive through 0 to negative, let's say, then that means that the second derivative is negative, and that represents a concave downward section, or concave downward on the interval. Just like if the second derivative is positive, then the graph is concave up on that interval. Okay, I'll just pause there, let you copy that down, and let me know if you have any questions about that. Okay, so let's get practical now and do an example. Here is a polynomial function. So this is a cubic function, okay? So it's going to kind of rise, come up, and come down, and go up again, looks like. Okay, we know what a cubic function kind of behaves like. y equals x cubed, goes up and levels out real quick and then goes up some more. So, but when you have other terms like this involved with a cubic function, chances are that's going to go up and it's going to come down and it's going to go back up again. All right, so the positive leading coefficient, you have in your mind what this graph might generally look like. We don't know intercepts, we don't know local max or mins or anything yet. What we're trying to find here is just focusing on what intervals is this graph concave up and what intervals is this graph concave down. So we need to examine the second derivative. So for A, okay, let's write some steps here. Steps. Okay, find second derivative. All right, that's pretty basic there. Find second derivative. So as we know, we need to go through the first derivative to get the second derivative. So this is what, 3x squared minus 6x plus 4. Okay, and then minus 0 there. So this is first derivative. Second derivative is the derivative of the derivative, the rate of change of the rate of change, which is expressed as 6x minus 6. Okay? We good with that so far? Now we can factor this, right? That's totally good. If we want to factor, we always should factor if we can. So we actually have 6 times x minus 1. So we have two factors technically there, and one factor is just plain old 6. It does not have a variable in it, so there will not be a solution to, there won't be a 0 for the second derivative on this factor, but x equals positive 1 is going to be important later, and even now. But so we can see that there will be a change in the second derivative at some point here. So find second derivative. Perfect, okay? After that, we're going to factor and perform, you guys are going to love this, sign analysis. Remember sign analysis? Everyone's favorite. Yeah, okay, great. Okay, factor, perform sign analysis. So sign analysis looks like this. We've got our elongated L shape. This is the number line here. We're going to put, I'll change color so it's easier to distinguish. We're going to put our factors on the side here. And we're going to find out where these factors are 0 and positive and negative. Well, positive 6 is positive everywhere and it's never 0. So that's what that line looks like. This factor is 0 at positive 1, as I mentioned. It's negative before that. Any number that's negative, or that's less than negative 1, or that's less than positive 1, like 0. 0 minus 1 gives you a negative answer, negative value for this. So that's why we put negatives there and positives over here. Hopefully you remember sign analysis. But again, we're doing sign analysis on the second derivative, so we will be able to tell the intervals for which the second derivative is positive and negative. So y double prime, we'll remind ourselves that that's what we're examining here. And because these are factors multiplied together, I'm going to multiply a positive times a negative for this space here. And that's going to give me a negative value all along here up to 1. A positive times 0 will be 0. And a positive times a positive in this interval will be positive. Okay? So where is it concave upward and concave downward? Now we can determine, so here, step 3, perform sign analysis, state interval of positive y double prime. That is, that's concave up. And negative y double prime, and that is concave down. Okay, so second derivatives, sign analysis, state intervals. Okay, so for A here now, we've determined that this graph is, and you can abbreviate C dot U dot like we did in pre-cal 30 with me, that's fine. Concave up. Now the interval, you should use interval notation, that's the easiest way to do it. So it's where it's positive, so it's concave up at the interval, and this is going to be an open interval from what, 0 to positive infinity. Okay? Could you say x greater than 0 for this one? Yeah, it's pretty easy. The interval notation is going to be way easier when you have lots of different intervals. Yep.
Is it at 1 negative infinity?
Oh, sorry. Yeah, that should be 1. On 1. Sorry, this is really small for me to see. There you go. Thank you. From 1 to positive infinity. It's this, up here, this interval. Thank you for noting that. That's where it is positive. So concave down, C dot D, concave down, and that's going to be where the second derivative is negative from negative infinity to 1. Okay? All right, questions there? Any questions there on that one? Concave up, concave down. B, now finding the points of inflection, that's where the concavity changes from either positive to negative or negative to positive. So we can see that we have a change from negative to positive here at this point, x equals 1. So for B, x equals 1, we do have to write this as a point, so we have to find out what y equals, but it's at x equals 1 is where this point of inflection is going to be. So y is, that's 1 cubed minus 3 times 1 squared plus 4 times 1 minus 5. So that's going to be 1 minus 3 is negative 2, and positive 2, and negative 3, looks like. So the point of inflection, and this is fine to write this as P, I'm okay with abbreviations. POI, point of inflection, 1, negative 3. And yes, as we move through this chapter, I do need you to write the point, not just the x value, because you're going to be graphing this, so you need the y value too. So make sure you do that. So here's A, and here's B. Okay, are you with me on the point of inflection there? We're taking a look at the sign analysis. So the sign analysis is actually kind of important where it changes. Okay. Now, the other thing to mention here too, at this point, if at x equals 1, if this was infinity, like if this was undefined, then there's no point there, so there's no point of inflection. Okay, so you got to be careful when you state the point. Make sure that point is actually on the curve. And so, you know, we checked that really. We put 1 here, 1 there, and 1 there. We got a y value. Okay, great. So it exists, okay? If you put in a 1, it's some kind of rational function, you get divided by 0 or something, that's not a point then. You have to really look at what's going on there, and there might not be a point of inflection, okay? Even if it does change. Because the case of, let's see, like if you have a vertical asymptote, right? And you have a graph that is concave down on this side and concave up on this side, guess what? It changes, but there's no point. There's no actual point where it changes. It's different than this, concave up to concave down. See, it's continuous, there's a point. Point of inflection, yes. Point of inflection, no, not here, okay? And that will come up too. So we do have to kind of use our heads there and make sure that the point exists if we want to state a point of inflection. Okay, finally, use this information to sketch the curve. Okay, we'll use this information to sketch the curve. It looks like from other things that we know, and what else do we know? Well, we know, as I mentioned before, that it's cubic, and this is a positive leading coefficient, so our end behavior is going to be such that it starts down here and ends up here somewhere, right? We do have, at x equals 1, a change of concavity at x equals 1, and the point negative 3. So negative 3 now. Okay, we just have 1 point of inflection. Okay, and do we know an intercept or something? An intercept is negative 5. So let's say here's the intercept of negative 5. So we don't know exactly, you know, how this works. So negative 5, I guess this is going to be up here. Okay, so we don't know much about this graph, but what we do know is this, and this would be as much as you'd be responsible for. It's going to be concave down. It's going to pass through this intercept. It's going to be concave down up to this point, and then it's going to flip to concave up. And it's going to end in this quadrant. So we know all that. We don't know what the max and min is. We don't really know much more because we haven't done the study. It could actually look like this, right? There could be some local max we don't know about or local min that we don't know about. Could technically look like that. We don't know. We'd have to do some more examination, but at least something like this. Concave up before that, concave down before this point of inflection, concave up afterwards. That's as much as we know best you can do. But you can kind of see that if we examine local max and mins, more intercepts, vertical asymptotes, horizontal asymptotes, you're going to get a very accurate picture of what this graph looks like. Okay, did I finish my steps? Probably not. State the interval, okay. So 4, let's do number 4 here. Step 4 on the point of inflection, okay. From sign analysis, determine POI as the point on the curve where the sign for y double prime changes. Determine. Let's change that to an actual word. Determine. There we go. Okay, does that make some sense? Whoops. I'll zoom out a little bit. So, yeah, that doesn't help, does it? No, not really. Okay. So that's the 4th step right there. So you get everything at once there. All right, any questions about that example? Please note that there must be a change in the second derivative. If it's negative and then negative again, even if there is a point in between, that's not a change. That's not a difference. That would be more like a cusp, I guess, right? You'd have something like this. It would be up and then up again. So that's not a change. That's okay. So it has to be a change in the sign there. Okay. All right. There are other examples that are in your textbook. I would encourage you to look at that. There are examples of rational functions, which will give you some, asymptotes maybe like I drew before there. So let's get back to a regular view here. So in your textbook and other places for your own study, if you take a look at graphs like a 1 over x or something, right, where you have this and this, okay, and you have an asymptote here, okay, so y equals 1 over x. If you go through the process, what do you'll find? You'll find that this is concave down, this is concave up. So it's changing concavity, but there is no point of inflection, as I mentioned before, okay? So the second derivative could equal 0, but also just like critical numbers, right? Critical numbers where the first derivative equals 0, x values where the first derivative equals 0, or the first derivative is undefined. Those could be critical values, so max or mins. So it's the same thing for second derivative. You may have sign analysis, and you may have negative, 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 and then you may have infinity, and then positive, positive, positive. Okay, so that would be the case here. The second derivative is undefined because there's nothing there. There's no concavity there. There's no point there at all. So what happens? Well, we have concave down before that, and concave up after that. And so it might look something like this. There is a change, so concavity is changing, but there's no point of inflection here in this case. All right? So just keep that in mind. And like I say, I'll let you look up some examples, read from your textbook, or look up some videos. I have some videos you can look up for more questions. All right, so I'll give you your assignment, and then you can let me know if you have any questions on concavity, second derivative, point of inflection today. Okay, so on MrMathWell.com, your course page, we're looking for Chapter 5, curve sketching. Here's your Chapter 3, or Section 3 assignment. There you go. So this is what we've done so far in the chapter. Yeah, so 5.4, a little more work on concavity points of inflection. I believe 5.4 is the second derivative test we'll focus on there. I believe, yeah, second derivative test. And then 5.5 is putting it all together. So it's 5.5 is the summary of everything we've learned, 5.155 for curve sketching. Okay? And if you want to avail yourself to some videos here, go right ahead. Let's see, what do I have here? So far, I'm going to, oh, what the what? Chapter 7. Oh yeah, there's a curve sketching video you might want to watch there. That's pretty corny. So 5.3 concavity, you have a few videos there. I'll probably put this new one up. There's number 4. I have up there too if you have trouble with number 4. Okay? All right, use the rest of the class here to finish your homework.